great pleasure. It's a great honor. I'm particularly happy and feel grateful of having the chance to celebrate Roger here. Roger has been an intellectual hero for me all through my life because he's not a normal great scientist. He's something else. I've been always struck by two things about Roger. On the one hand, his wide, extremely wide, the wide scope of his interest and the wide area of the part of our current knowledge that he mastered in death. I mean, his popular book that many of you know show that. If you think about Road to Reality, one of his books, which is probably one of the hardest of the popular book, the photography he gives of what we know and we don't know about the physical world today, I think is unique in depth and wide angle. But next to that, Roger has been always an extraordinarily creative and courageous thinker that has always gone in directions which were quite far away and independent from the common way of thinking. You see, my view of what's going on in physics today is that there's a lot of wild speculations about reality, the universe, and everything. Many dimensions, many fields, many particles, many symmetries, but it's always all of the same. Dimensions, particles, symmetries. Most of Roger's ideas go in other directions, and has been that for years, and is still going on. This Roger's creativity, sometimes leaving the community perplexed. What is he doing? Because what he's proposing is often a truly new way of thinking about reality, and that's what I've admired of him, and that's why I'm so happy today to be able to participate, to celebrate him. And I want to do that by telling you a story. When I was asked to give this lecture, I said yes immediately because I have a story to tell, and it's a story of spin networks. And I think it's an interesting story because it shows this aspect of Roger's creativity, his capacity of thinking in new direction, completely transversal to where people are going, and to anticipate also where the field is going. So the story I'm giving you is a story of one idea, one object, spin networks, which today is playing a big role in quantum gravity. Today, in that part of the research in quantum gravity that goes around loop quantum gravity, there is maybe hundreds of scientists in the world that use spin networks as a daily tool for describing quantum properties of space-time. And spin networks came into, I'll tell you what they are at some point precisely, but spin networks came into the theory in the middle of the 90s from a long and complicated mathematical work within the complicated structure of loop quantum gravity, and emerged as a proper language for describing quantum space-time. This is, I was deeply involved in that work, and the appearance of this tool for describing quantum space-time changed completely the way we were dealing, and also we were thinking about the microstructure of space-time. This was the middle of the 90s, except that the spin networks were actually introduced by Roger Penrose 20 years earlier in a paper in '71, where there was no general relativity, no quantum theory of gravity, no big and complicated mathematical story. There were just some key ideas of how geometry and quantum could stay together. And out of that, there was the beautiful construction of this mathematical object that later on turned out to be so key and central in the construction of what is today one of the main attempts to do a quantum theory of gravity. So the story I'm going to tell you is, first of all, that paper. So I'll start from the 71, and what is in that paper by Roger. I have a copy here. It's I don't think many people have read this paper because in the community everybody knows about that, but people don't go back to that paper. It's a marvelous paper because it just focuses on the key physical ideas which is needed to bring two apparently contradictory things together. I'll try to show you how and what. So I will explain what is that paper, and then at the end, I will tell you how the spin network have evolved today in a form which is essentially the same, also a little bit richer and with some additional mathematical structure, but not much. But the core idea is the same, and how they are today a tool for thinking about quantum spacetime. So that's the plan. So first of all, let me tell you what a spin network is, because it's a very simple object. Spin network. I hope I'm writing large enough so you can see, but I'm not going to write much. It's just a few pictures, and also I'm going to talk to most of the audience. Are not mathematicians as far as I see and understand, but I see in the audience some friends and people I recognize which know more mathematics than me or more philosophy than me. Or I'm not talking to these people. I will add here and there a few technical comments just to connect with the mathematics which is behind that, but I will stay very basic. So what is a spin network? A spin network is a graph with some numbers. Some integer numbers. So a graph, it's a set of points connected by lines. So these are points connected by lines. Point, lines, where it doesn't matter how you draw it. It only matters how many points you have and who is connected to who. So whether I draw a spin network, say 2 points like that, or like that, it's the same object as a spin network. 2 points connected by 3 lines. And on the lines sits integers, numbers. So say 2, and the reason I'm looking here because I want to draw the same spin network that Roger had in his first paper, just to see his own initial picture of a spin network for 1, 1, 0. I guess you need a 1 here too. So that's it. This is spin network. We call it alpha. So it's a graph, an abstract graph, with some integers on it. That's the object he introduced in the 70s, and attached to it, there's a little bit of mathematics. You can compute just out of this data the connectivity of the graph. The graph and the numbers, you can compute a number, which is called the value of the spin network, which is a certain number, which you can do just by doing something with these numbers. I'll tell you later how exactly you compute this number. This is the object I'm going to talk about for this 30, 40 minutes. I'm going to talk. Now, where does it come from, and why Roger introduced it, and how it then became a key object for doing quantum gravity? The problem, the physical problem, which is the problem of quantum gravity, is the quantum aspect of space. So space is whatever is between my hands. What's in in these 2 feet or whatever. So if you imagine what is there between my hand. If you imagine there's air, you take away the air, there's some light, some goes through. Imagine you zero all the light, all the fields. Something remains, that space. And that space has a structure, which is described by elementary geometry to some approximation, or to a better approximation described by Einstein general relativity, because actually there's some curvature, something like that. So we know a lot about the space and how to describe it. But we also know that precisely because of general relativity, the space has dynamical properties, can bend, can curve. So it's a field, it's a physical field. And as such, it must have quantum properties. So we expect that it has quantum properties that show up somehow. And the problem of quantum gravity is understand what are these quantum properties. And the quantum properties show up in a small scale, at a very small scale. So the question is, what is the quantum property for space here between my hands? And what Roger did is to come up with a hint, an idea of how to describe these quantum properties by taking some key aspect of space and key aspect of quantum and bringing them together. So what are the key aspects of space on which Roger did focalize? What are the key aspects of quantum? Space, it's a set of points. Given 2 points, you can measure the distance. So you can measure distances. Distances, of course, satisfy all the relation you know well. I mean, if this, this is 5, this is 5, this is 4, this is 3, for instance. This is a right angle, and so on. A key aspect of space is continuity. It's continuous. Space, as we describe it in standard geometry, is continuous. Space in general relativity is continuous. You can look at the property of space from another perspective just by picking one point and looking around. And you have all the possible directions. Let me just take the pen. All the possible directions from one point. And these directions also are continuous. So there's a continuity of possible directions. And you measure direction with angles. So you have to measure the angle with respect to something. Also distance, you have to measure the distance with respect to something. So distance is always a relational property between 2 points. And angles is a relational point between 2 directions. But the angle is continuous, right? It can go from 0 continuously to pi half to pi, and so on. So continuity is a key aspect of space, and one way it's realized is the continuity of possible directions in space. That's space. Now let's look at quantum. Quantum, there's something which is sort of goes the other way around. What's quantum mechanics? Quantum theory. Well, you all know that nobody knows what's quantum theory, but one way of summarizing quantum theory is to capture it in 3 steps. One way I like to think about quantum theory is to capture it in three main sort of discoveries about the world, which are the basis of quantum theory. In Oxford, there was somebody who doesn't like to think quantum theory this way, but I'm definitely not going into the discussion of how to think about quantum theory. This is taking standard textbook quantum theory as it is. So one way is probability. Quantum theory is discovery that generically we cannot predict. We cannot know sufficiently about the state of the world to predict what we're going to see with certainty. You always have some irreducible probabilities that you might interpret in different ways, but is always there. Which means that if we know something about directions, we are going to have, in a quantum theory, to be able only to predict probabilities for angles. This is going to come back. The second is relationality. In quantum theory, in the standard formulation of quantum theory, you always have a quantum system and you measure its property, and there's some apparatus, some observer, something else that interact with the object, and you measure this property as seen by the apparatus. That's perhaps the most mysterious aspect of quantum theory, but property is always relational to something else. That's not going to affect much other way of thinking about space, because I just said that we can focus on a feature of space which are relational, right? The distance between 2 points is a relation between 2 points. The angle, and how you think about directions is always, by measuring direction meaning measuring angles between 2 directions. One direction by itself doesn't mean anything unless you compare it to something else. So that's okay, I mean, just put this on the back, but let's focus on the third and key point, which is discreteness. Discreteness as opposite to continuity. So a lot of quantum mechanics is the discovery that there is discreteness in the world. The things are discrete. They're not continuous. They only can take certain values, right? The light that comes to me is well described if I neglect quantum mechanics as a continuous wave whose amplitude can take any continuous possible value. We know from quantum mechanics that if we look in detail, the light that arrives somewhere arrives actually like a raining of droplets of photons, quanta of space. So there is a granular aspect in light, which is the photons. And then the orbits of the electrons around an atom cannot have any energy, but only certain energies. So most observable quantities in quantum mechanics take only certain values and not others. And to some extent, one could even say that the ones who don't are extreme case or limiting case. So discreteness, it's a core aspect of quantum mechanics. It gives it a name, quantum. Quanta are chunks. A quantum is a discrete bit of something. So I'm going to focus on this one because it's clearly something that at first sight it seems to clash a bit with the continuity of the property of space if space has to be quantum mechanical. And in fact, those of you who know a little bit of quantum mechanics, who've taken a course on quantum mechanics, have taken a course in what is called angular momentum theory, and know that there is a precise sense in quantum mechanics in which the angles between two things are not continuous but are discrete. And this happens when you are thinking about the direction as the direction individuated, picked up by something that rotates. If something rotates, it rotates around an axis, and the axis picks up a rotation. Let me put it visually. This is something that rotates. Right? And it has an axis. And it can have this axis, or if I turn this way, it has this axis. So any rotating thing picks up a direction. And conventionally we say that rotate this way, the axis this way. If you rotate this way, the axis this way. So in any classical rotating object can rotate with an arbitrary angular velocity and with an angular direction of its axis of rotation. Well, in quantum mechanics, because of that discreteness, you show, in fact, you learned in elementary courses in quantum mechanics that that's not true. Everything that turns has discrete angular momentum, which is the measure of the axis and the amount of its rotation. Discrete in two senses. The velocity is discrete, so given the mass of it, you have a certain possible velocities possible. And more importantly for us, you don't have the possibility of all possible directions, but only to some of them. How many of them depend of the total velocity. So for all of you, for those of you who have studied quantum mechanics, the total angular momentum is quantized, so the length of this is quantized, but the component of the angular momentum in one direction, Lz, is also quantized. So if you want to know whether the direction is up or down or in the middle or continuously between the two, in quantum mechanics you cannot get all continuity, but you can get only some possible values. For an electron, just 2, up or down. For an atom with spin 1, just 3 possibility, or 4, and so on. And this is the quantization of angular momentum. This is well known, studied in mathematical classes, it's kind of physical classes. It was discovered back in the 30s, and there's a lot of experimental support to that, Stern-Gerlach experiment, all sorts of things. You measure the angular momentum of something, it comes out quantized. All right, so far it's just standard thing. Now, back to space. Roger's point in the 70s was, wait a minute, if angular momentum is quantized, directions are quantized, that's likely to be a property not just of a rotating object, but of space itself. Space itself must be such that directions are quantized. Because space itself, this is a general properties of the geometrical variables that describe space. If these geometrical variables that describe space are quantum, they have to have this property, and I should be able to find discreteness. So Roger was trying to build up a way of thinking about quantized direction, discrete directions, out of which to derive continuous space only in some limit. Instead of seeing a continuous space and then some quantum stuff on it, try to have continuous space emerge from purely quantum underlying thing. And in fact, in the paper, he was just going to the most basic thing at all and says, well, discreteness as the basic is just counting, 1, 2, 3, 4. It's just saying how elementary bits can stay together, so it's combinatorics. And the question he put at the beginning of the paper is, can I get space from combinatorics? And the first reaction you have is no. I mean, space, continuous three-dimensional space is most distances all from combinatorics you can imagine. And at the end of the paper, you see, no, you can get key aspect of space of all possible directions, just from combinatorics. And that's the tool. And let me show how he did it, because it's beautiful. There's a few lines. It's actually quite simple. So the idea is that imagine that each one of these lines is a direction. And somehow, given one line splitting in 2 lines, of 2 lines going to 1 line, this is sort of combination of direction, or whatever it means. In quantum mechanics, a combination of angular momentum. And imagine these numbers here are the possible discrete value of total angular momentum. So how much something is rotating. Nothing here seems to talk about directions. So there's no directions here. Can I get directions out of that? Can I compute angles out of that? And then remember, directions are always relational. Something is related to something else. But if I have one spin network here and another spin network there, it makes no sense to talk about relative angle between the two, because there's no connection between the two. what could make sense is think about the angle between this direction and this direction. So the question that Roger asked is that you have a spin network here, some complicated graph, of two particular lines coming out, one with a number A with a number B. Can I define the angle between these two? And here is a formula for the angle between the two, only based on the spin network sitting inside here. More precisely, probability. He writes a formula for having the probability of one or the other values of possible angles between the two, given the spin network here. And how it does it? Let me be technical for 1 minute and actually give the core of the story. You take this spin network, you add a point, and you do another one with an x. And you think that this is direction A, this is the direction B. So this is direction A, your reference, and the other is direction B. And you ask how they combine. And they can combine depending on the angle by sort of summing up or by subtracting one from the other with all possibility between the two. So this x here can be any number between a plus b and a minus b, thinking of two vectors with an angle between them. And each number in between, of course, is clearly related to an angle, theta, between the two, which is given by sort of elementary geometry. And then you want a probability of having that angle, theta, just in terms of these two. And Roger writes a formula, which is some simple formula, which is something related to the value of this spin network divided by the value of this spin network. So let's call this beta, and this alpha is sort of the ratio of something which is the norm of alpha, the norm of beta, with some coefficients here, which I'm not writing, just depend on A, B, and X, where the norm of a spin network is just the value of the spin network square. There are some technicalities, not important. Well, the spin network square is by taking two spin networks, you join all the free ends, and you compute a number. Let me just tell you what is this value, because it's going to play. So the value of a spin network, and now see how pretty it is and how really combinatorial it is. I don't want you to feel the details, so I want you to get the sense of it. Imagine you have a simple spin network here, 2, 1, 1. I'll tell you how to compute the value. The value is given by a sum divided by a product, and you do like that. Every time you have a line, a link with a number n, you copy it with n little lines. So here you have 2. You rewrite it with 2 lines, and this is a single one, and this is a single one. And then when you have 2 or more, you copy this many times, and you symmetrize, or you can consider all possible permutation of the way these two are attached to these two. In this case, you have only 2 possibilities. So you open up your spin network in some expanded spin network with individual little lines, and then you count the number of closed loops here. You call it C. That case is 2. That case is 1. And you count the number of intersections. You see there's 1 intersection. Here is 0. Here is 1. And the value is the sum over this open up spin network of -1 to the I minus 2 to the C, divided the product on all the links of the number of the links, factorial. That's it. So I've given you the full formula with up to some details, of the angle. You get a formula for the angle purely combinatorial, out of just minus ones, plus ones, minus two, counting, nothing else. And then you show that this angle has all the property of the angle joined together with all the property of geometry. So you get a reconstruction of all possible angles and their relations from combinatorics. Now it seems magic is of course not magic, as Roger says in his article, and some of you immediately recognize, it's just reverse engineering representation theory of the rotation group. So that's what it is. It's angular momentum theory unpacked behind. This is the representation of spin 1, this is the representation of spin 1/2. This expansion is the fact that higher, for those of you who know the mathematics, higher representation can be written as tensor product of a smaller representation, of fundamental representation, and so on. So it's sort of a working back what we know from the theory of representation of rotation group. But if you forget all that, that's spectacular. You have just counting, and out of counting, you get the mathematics of angles. That was it for the 71 paper. And the core ideas, again, are space is continuous, quantum mechanics is discreteness. At the core, we expect space to be quantum mechanical. Can we get continuous space out of discreteness? And the answer is yes, at least for what regards the directions. We can by using discreteness, by using the fact that the property I'm looking for are relational, is one direction with respect to another one, and by not computing angles for probability of different angles, the core ingredients of quantum mechanics. 1971, Roger Penrose. 20 years later, 23 years later, right here, you see here, change color. 1995, spin networks enter loop quantum gravity. Just to tell you where we were, 1985 roughly, it's loops, the beginning of loop quantum gravity. Here the story, it's I'm not going to cover the full story, but just to orient you where you are. It's a long and complicated story of the quantization of general relativity. It starts with Dirac, it starts with Einstein, goes to Dirac, the rewriting general relativity in the Hamiltonian form, Arnovit, Devon, Misner, and so on. It's a long and complicated and very technically heavy story with the idea of doing the Hamiltonian formulation of general relativity for doing its quantum version, and therefore going to the quantum properties for space-time. And then there's in the 60s, there is a very celebrated work by two American physicists, John Wheeler and Bryce DeWitt, who write the Wheeler-DeWitt equation, who is a sort of Schrödinger equation for general relativity. It's a very, very complicated infinite set of functional differential equations coupled, which nobody knows how to deal with. And then magically, Ted Jacobson and Lee Smalling in the 80s find solutions to this equation. And these solutions are labeled by loops, closed lines in space. And nobody knows how to interpret them. And that's when I entered the game, and I remember the confusion at the time. Somehow, they represent an excitation of space where you have geometry along this loop and nowhere else, whatever. And during these 10 years, there was a lot of discussion about the interpretation of these complicated loop solutions. And two key steps were taken by a Polish mathematician, Jurek Lewandowski, and an Argentinian physicist, Jorge Pulling, who realized, first of all, that the theory is not complete unless you consider loops that can cross themselves. And the theory is not complete unless you consider also the possibility that loops run over themselves. So they go through the same path, so to say, whatever that means. That was what Jurek understood. And what Pulling understood is that these crossing points, these nodes, are crucial because the state represented by this funny solution of the Wheeler-DeWitt equation have, in a very precise technical sense, zero volume unless there are these nodes. So nodes are essential. The name loop of loop quantum gravity is a little bit misleading because if you only have loops, you can't get anything interesting. And the volumes sit here. Which gives a sort of picture like this one. If you have a spin network, roughly, so imagine you have a spin network. Sorry, imagine you have a graph. Then the way you have to think about is that the volume sort of sits on these nodes. And what this really represents is a chunk of space here, chunk of space here, chunk of space here, attached to one another. And then in '95, Lee Smalling was visiting Verona, and we were working on a technical problem which is trying to understand the actual geometry in these states. And in particular, we were thinking of this problem here. Suppose this is a chunk of space. Let me just draw tetrahedron for simplicity. And this is another one. And they're attached to this common face, this common triangle. The question we were asking is, how big is this area? And we studied this question with standard kind of calculation that you do in quantum mechanics. In quantum mechanics, you compute this discreteness, which is common through a technical calculation in quantum mechanics, which is called the spectral analysis of a Self adjoint operator. And in the theory was about gravity, and gravity is geometry, so it was about geometry. So the geometry, the area of this, it's a observable of the geometry, and the geometry is a gravitational field. So the gravitational field is a quantum field, so there was a quantum operator associated to it. And we studied the mathematics of these quantum operators, of all these quantum operators, for all this. And what we find that the spectrum is discrete, and so we can look technically the eigenstates of this operator. So the quantum state of space that have these particular values of the area. And this particular value of the area are labeled by integers. So we can write the states with integers here, 1, 2, 1, 0, 3, etc. Where these numbers represent the area of this triangle, which of course defines a direction space. And what if we want to know the angle between the direction of this and the direction of this? So the direction of the face of this chunk of space, which goes out, and this one, well, not surprising, is given by Penrose formula. And the possible angle between the two are discrete, and the possible areas are discrete. So here we are taking out from the theory a description of microstructure of space where there are small chunks of volume that defines directions, but this direction are only defined relative to one another, and probabilistically, and can only take discrete values. And at the core of loop quantum gravity is a mathematics which is essentially just a bunch of representation theory of the rotation group, which is exactly the object that Roger has introduced more than 20 years earlier, without any consideration of generativity, of Wheeler-DeWitt equation and all operators or anything like that. And nowadays, the spin networks which are used are essentially the same thing. They're just built with the same mathematics, a little bit some technical complication, but are the same thing. So I found this story marvelous. Marvelous because what Roger had done in the 70s was sidestepping all the construction of the theory on the basis of the details of our current knowledge about the general relativistic structure of space and quantum mechanics, and just zoomed down to the core idea: continuity, discreteness, relationality, and found a natural way of putting them together. Today, let me sort of move toward the end. Today, this spin network provides a picture of the small structure of quantum space-time, and I would like you to appreciate what I think is the beauty of this picture, which can be said in the following way. This quanta of space, these things which describe the elementary quantum space. This is a little chunk of space, This is the connection between the two. So this number here says how big is the connection, how large is the area between the two, and the relative direction. These are not like particles of quantum field theory, like photons. These are not quanta that move around in a given space. These are quanta of space itself. So these do not sit into a space. You cannot ask what is in between two of these points. These are the elementary thing that build up the structure in which we live, which we at a very large scale perceive as a continuous space. This is a way of doing physics which takes us suddenly completely away from field theory as is done by particle physics, by people doing electromagnetism, where the main ingredients are space, a priori, continuous, time, space-time, Poincare group, energy, momentum. All these quantities disappear from the theory because there's no space, there's no time. I'm not talking about time here, but there's also no time in the same sense. There is no energy, there is no momentum. The quantum numbers that describe something don't have a p, a momentum, like in particle physics, or an x, or a position, because position momenta are only in the small things relatively to one another, but not relatively to a background structure, which is space. The core physical intuition behind loop quantum gravity is this, and it was largely anticipated by Roger. So that's a story I wanted to tell you, and I think to me has been a great story because a lot of my scientific career was developing around the construction of this theory, around the set of key ideas which I've tried to explain, and it has been a privilege to sort of walk in the step of Roger, and I want to take this opportunity to say to Roger, thank you very much for this and for the many other wonderful ideas he has given us. Thank you.